General Mixed Mode Single Output. DDCC-based Universal Biquad Filter. Abstract. This paper presents a general mixed mode, including voltage, current, transadmittance, and transimpedance modes, universal filter using only 3 single output differential difference current conveyors, DDCCs, 2 grounded capacitors, 3 grounded resistors, and 1 floating resistor. The proposed circuit can realize all 4 modes' 5 universal filtering responses: low pass, high pass, band pass, notch, and all pass, from the same topology. The proposed circuit uses only single output DDCCs with simpler implementation configuration than the multiple output current conveyors. This represents the attractive feature from chip area and power consumption point of view. Moreover, the proposed circuit has no need of component matching constraints for all 5 universal filtering responses in voltage and transadmittance modes. Furthermore, the proposed filter offers the following features: I, using 2 grounded capacitors, 2, no component value constraints except the current/transimpedance all-pass response, 3, no need of extra inverting or non-inverting amplifiers, 4, no need of extra current replicas degrading the final output impedance, and v, low active and passive sensitivity performance. H-SPICE simulation results confirm the theory. Keywords: active filters, differential difference current conveyors, DDCCs, general mixed mode, universal biquad filter. Introduction. The applications and advantages in the designing general mixed mode universal biquad filters have received considerable attentions in recent years. This is because general mixed mode operations, including voltage mode, VM, current mode, CM, transadmittance mode, TAM, and transimpedance mode, TIM, i.e. 4 modes, such as TAM and TIM, can play a very important role for transferring from VM to CM and vice versa, respectively. Therefore, the general mixed mode universal biquad filters with input currents or /n voltages and output currents or /n voltages, are worthy of research and presented for the use of any filtering requirement, which is compatible with modern microelectronic systems applications, such as controls and voice and data communications, where consideration of size and weight make the use of inductors prohibitive. In the past several decades, many single-mode, dual-mode, or mixed-mode filters using different active elements have been presented 1 to 51. The filters consist of more modes and filtering functions, meaning more applications for which they can be used. However, only several circuits 1 to 4, 6 to 8, 10, 12, 15, 17, 22, 24, 25, 27, 31 to 34, 36, 38 to 40 can realize all 5 universal filtering functions: low pass, high pass, band pass, notch, and all pass, in VM, CM, TIM, and TAM. Such filters are referred to in this paper as general mixed mode universal filter. The general mixed mode universal filter structures employ at least 4 active elements in 1 to 4, 12, 15, 17, 25, 27, 31, 32, 36, 39, 40, and need some matching conditions for realizing some VM or TAM filtering functions 1 to 4, 12, 15, 17, 25, 27, 36, 39, 40. For example, in 2012, Lee proposed a multiple mode, i.e. general mixed mode, universal filter 25 using 5 operational transconductance amplifiers, OTAs, as active elements and 2 grounded capacitors, for second order. The filter 25 can offer all 5 universal filtering functions in all the 4 possible modes. However, it needs component matching conditions for realizing VM and TAM all-pass responses. In 2013, it has shown that the mixed-mode universal biquad filter 27 needs to use 4 multiple output current-controlled current conveyors, MOCCCIIs, and 2 grounded capacitors. However, it needs component matching conditions for realizing VM notch, all-pass responses and TAM low-pass, notch, all-pass responses. In 2016, Two digitally programmable mixed-mode universal biquad filters were proposed in 31, 32, which can achieve many main advantages. However, the filter in 31 uses two multi-output second-generation current conveyors, MOCCIs, 6 digitally programmable second-generation current conveyors, DPCCIs, i.e. 8 active elements, 4 grounded resistors and 2 grounded capacitors. In 32, the filter uses followers with a minimal realization. However, the filter in 32 still needs to use 7 current/voltage followers, i.e. 7 active elements, 3 switches, 3 floating resistors, 1 grounded resistor, and 2 grounded capacitors. In 2018, Zanjani et al. Proposed a mixed-mode GMC biquad filter 39 with independently electronic tunability. However, the filter needs to employ 19 inverters as operational transconductance amplifiers and 2 grounded capacitors. In 2018, Tsukutani et al. Proposed a novel general mixed-mode universal biquad filter 40. However, the biquad filter 40 needs to use 5 DDCCs, 5 grounded resistors, and 2 grounded capacitors. Few general mixed-mode universal biquad filter structures employ 3 active elements of simple implementation configuration 6 to 8, 10, 22, 24. For example, in 24, the reported general mixed-mode biquad uses 3 differential difference current conveyors, DDCCs, 2 floating resistors, 2 grounded resistors, and 2 grounded capacitors. However, it needs component matching conditions for realizing VM, CM, TAM, and TIM all-pass responses. In 2017, the reported general mixed-mode biquad filter 35 uses only 3 current-controlled current conveyor transconductance amplifiers, CCCTAs, and 2 grounded capacitors. However, the circuit in 35 cannot realize notch and all-pass responses in TIM. Moreover, the UCTA is a complex active element. The applications and advantages in the designing current conveyor-based active circuits have received considerable attentions 1, 2, 6 to 11, 13, 14, 18, 20 to 24, 26, 27, 30, 31, 33 to 35, 37, 38, 40 to 50. Especially, the differential difference current conveyor, DDCC, 49, 50 has the ability to perform the operations of the intrinsic voltage addition and subtraction 47, 48. Therefore, it is very important for the design of general mixed-mode universal biquad filters 33. Moreover, the DDCC has simplest implementation configuration in all of the other complex current conveyors, such as fully differential current conveyor, FTKI, current-controlled current conveyor transconductance amplifiers, UCTA, differential difference current conveyor transconductance amplifier, DCT, differential voltage current conveyor transconductance amplifier, DCT, digitally programmable second-generation current conveyors, DPCCIs, and dual-X current conveyor. Differential input transconductance amplifier, DCDA. The use of a FTKI can be divided into 2 separate DDCCs. A UCTA can be produced by cascading a UCI with an ODA. Similarly, a DCT, or DVCT, also can be produced by cascading a DDCC, or DVCC, with an ODA. Therefore, each of them can be regarded as 2 basic active elements. In 13, Li and Chong proposed a single FTKI-based mixed-mode biquad filter 13. The circuit 13 uses only a single FTKI, 3 floating/grounded resistors, and 2 grounded capacitors. In 2017, the reported mixed-mode biquad filter 37 employs only a DCDA and 4 passive components. Although single active element-based mixed-mode biquad filters have been proposed in 13, 37, both circuits 13, 37 are not general mixed-mode universal filters. Moreover, both used active elements, i.e. FTKI and DCDA, are complex active elements. There are 3 general mixed-mode universal biquad filters using 2 active elements 33, 34, 38. In 2016, Lee proposed two general mixed-mode universal biquad filters 33, 34. The filter in 33 uses 1 FTKI, 1 DDCC, 6 grounded/floating resistors, and 2 grounded capacitors. The circuit has versatile input/output functions 33 which can offer all 5 universal filtering responses in single input multiple output, SIMO, and multiple input single output, MISO, types, respectively. The circuit in 34 uses 2 plus type FDCCIIs, 5 grounded/floating resistors, and 2 grounded capacitors. The circuit 34 has no need of any matching conditions, which includes no need of component and input matching conditions. Similarly, in 2018, the reported mixed-mode biquad filter 38 also uses 2 FDCCIIs, 4 floating/grounded resistors and 2 grounded capacitors. Although the filters in 33, 34, 38 use only 2 active elements and can achieve many important advantages, it was shown that the use of the complex active elements and many resistors was unavoidable. In 2013, the reported mixed-mode 28 biquad filter employs only 2 voltage differencing transconductance amplifiers, VDTAs, and 2 grounded capacitors. The circuit can realize all 5 universal filtering functions in VM and TAM, but at 28 has not been operated in CM and TIM. In this paper, the proposed circuit uses only 3 single-output DDCC, 2 grounded capacitors, 3 grounded resistors, and 1 floating resistor, which can realize general mixed mode, including VM, CM, TIM, and TAM, all 5 universal filtering responses, lowpass, LP, highpass, HP, bandpass, BP, notch, NH, and allpass, AP, from the same topology. Over the last decade, the general mixed-mode universal filters have been presented in the literature 1 to 4, 6 to 8, 10, 12, 15, 17, 22, 24, 25, 27, 31 to 34, 36, 38 to 40. With respect to the references 1 to 3, 31, 32, 40, the proposed biquad filter employs fewer active and passive elements. With respect to the references 4, 12, 15, 17, 25, 27, 36, 39, the proposed biquad filter employs fewer active elements. With respect to the references 7, 10, the proposed biquad filter uses active elements of same number, but the proposed circuit has the following advantages: less component matching conditions, the use of only 2 grounded capacitors and no switches. With respect to the references 6, 8, 22, 24, the proposed biquad filter uses the same active elements, DDCCs, in same number, but the proposed circuit has the following advantages: no need of component matching constraints for VM and TAM, all 5 universal filtering responses, and the use of only single output DDCCs. Filters using only single output DDCCs have the advantages: I. No need of extra current replicas degrading the final output impedance, and 2. Simpler implementation configuration than multiple output DDCCs. This represents the attractive feature from chip area and power consumption point of view. With respect to the references 33, 34, 38, the proposed biquad filter uses the DDCCs with far simpler implementation configuration than FDCCIIs. 2. Proposed circuit. Fig 1 shows the proposed general mixed-mode biquad filter structure using only 3 single-output DDCCs, 2 grounded capacitors, 3 grounded resistors, and 1 floating resistor, where VIN1, VIN2, VIN3 are the filter input voltages and IIN1, IIN2, IIN3 are the filter input currents whose setting determine the filter functions as shown later: VOUT1, VOUT2, VOUT3, VOUT4, and IOUT are the filter voltage outputs and current output, respectively. Using standard notation, the port relations of a DDCC can be characterized by IY1 equals IY2 equals IY3 equals 0, Vx equals Vy1 Vy2 plus Vy3, is plus equals plus 9 and is equals dash 9. The current output has very high output impedance. Part I, VM and TAM universal biquad filters with 3 inputs and 1 output. If IIN1 equals IIN2 equals IIN3 equals 0, and VIN1, VIN2, VIN3 are given by the input signals, circuit analysis for Fig 1 yields the following VM and TAM universal transfer functions. VM universal transfer function, 1. TAM universal transfer function, 2. Specializations of the numerator in 1 and 2 result in the following VM and TAM 5 universal filtering responses from voltage output and current output as below. Note that it is no need to impose component choice for realizing any filtering responses. Moreover, no inverting or non-inverting amplifiers, for special input signals, are needed in the realizations. Part 2, VM universal biquad filter with 1 input and 4 outputs. If IIN1 equals IIN2 equals IIN3 equals 0, and VIN2 equals 0, VIN1 equals VIN3 is given by the single input signal, circuit analysis yields the following VM filtering responses. Examining 3 and 5 show that the voltage difference between VOUT1 and VOUT3 yields an all-pass filtering response. VM all-pass, 7. Note that it is no need to impose component choice for realizing any filtering responses. Moreover, no inverting or non-inverting amplifiers, for special input signals, are needed in the realizations. Part 3, CM and TIM universal biquad filters with 3 inputs and 1 output. If VIN1 equals VIN2 equals VIN3 equals 0, and IIN1, IIN2, IIN3 are given by the input signals, circuit analysis for Fig 1 yields the following CM and TIM universal transfer functions. CM universal transfer function, 8. TIM universal transfer function, 9. Specializations of the numerator in 8 and 9 result in the following CM and TIM 5 universal filtering responses from current output and voltage output as below. In 4, a low-pass notch and a high-pass notch can be obtained by tuning the grounded conductances G1 or G3. Note that it is no need to impose component choice except CM/TIM all-pass response. Moreover, no inverting amplifiers, for special input signals, are needed in the realizations. Inspection of 1, 2, 9 show that, in all cases the parameters 0, 0/Q, and Q are given by. From 10 and 11, the parameters 0 and 0/Q can be orthogonally adjustable by tuning the grounded resistor R2 for 0/Q first and then resistor R1 for 0 without disturbing parameter 0/Q. However, 10 and 12 show that the parameters 0 and Q are interactive. The technique to obtain the non-interactive filter parameter control can be suggested as follows. 44. For the fixed-valued capacitors, the 0 can be adjusted arbitrarily without disturbing Q by simultaneously changing resistor R1 and grounded resistor R2 and keeping the G1/G2 constant. On the other hand, the parameter Q can be tuned arbitrarily without disturbing 0 by simultaneously increasing 1/R1 and grounded R2 and keeping the product G1/G2 constant. 3. Non-ideal analysis. Taking the tracking errors of the single output DDCC into account, the relationship of the terminal voltages and currents can be written as IY1 equals IY2 equals IY3 equals 0, Vx equals SS1, S, Vy1, SS2, S, Vy2 plus SS3, S, Vy3, is plus or minus equals plus or minus A, S, 9, where A, S, and SS, S, represent the frequency transfers of the internal current and voltage followers of the DDCC. They can be approximated by the first-order low-pass functions 33, 42, 45 to 50. For frequencies much less than the corner frequencies of the DDCC, all A, S, and SS, S, are real quantities of magnitude slightly less than 133, 42, 45 to 50. Assuming the circuit works at frequencies much less than the corner frequencies of A, S, and SS, S, namely, A, S, equals 1 EI and EI, EI1, denotes the current tracking error of the DDCC, and SS, S, equals 1 EV and EV1, denotes the voltage tracking error of the DDCC. Taking into account the non-idealities of the DDCC, 1, DDCC, 2, and DDCC, 3, we obtain the non-idealities as below. The denominator of the non-ideal general mixed-mode universal biquad transfer function becomes the point 0 and Q of the non-ideal mixed-mode biquad are. The active and passive sensitivities of point 0 and Q are from 19 to 23. The proposed general mixed-mode universal biquad filter has low active and passive sensitivities, not larger than unity in absolute value. 4.H-SPICE simulations. The CMOS implementations of the single output plus type DDCC are shown in Fig 242-49. Note that the DDCC has simpler implementation configuration than the FTKI, VDTA, TKTA, VKTA, UKTA, DKI, and DKTA. Moreover, the single output DDCC has no need of applying the realization of current replicas. Therefore, the proposed circuit has the advantage, no need of extra current replicas degrading the final output impedance. To verify the theoretical analysis of the proposed general mixed-mode universal biquad filter, the H-SPICE simulations with the NMOS transistor aspect ratios, W/L equals 5M/1M, and PMOS transistor aspect ratios, W/L equals 10M/1M, of Fig 2, using the TSMC 0.25M process for the proposed circuit of Fig 1, were performed with the component values, C1 equals C2 equals 4PF and R1 equals R2 equals R3 equals R4 equals 10 KO, for the general mixed-mode universal filtering responses, leading to a center frequency of F0 equals 3.9789 MHz and quality factor of Q equals 1. Their supply voltages are VDD equals VSS equals 1.25 V, VB1 equals -0.4 V, and VB equals 0.41 V. Fig 3 presents the simulated bandpass, lowpass, highpass, notch, and all-pass amplitude frequency responses of the proposed general mixed-mode biquad filter, operated in TAM with the normalized transadmittance magnitude equals 20 log 10,000 I out/Ven dB due to R equals 10 KO. Fig 4 presents the simulated all-pass phase frequency responses of the proposed general mixed-mode biquad filter, operated in TAM. Although not included in this paper, it can be shown that the other modes' simulated results, with the normalized magnitude, are very similar to the above simulated results. As can be seen, there is a close agreement between theory and simulation. Conclusions. Only using 3 single-output DDCCs, 2 grounded capacitors, 3 grounded resistors, and 1 floating resistor, to design a general mixed-mode universal biquad filter is presented in this paper. Filters using active elements with simple implementation configuration, such as single-output DDCCs, have the advantages of the lowest cost, power dissipation, chip area, and noise. Filters using single-output active elements, such as single-output DDCCs, have the advantage, no need of extra current replicas degrading the final output impedance. The proposed circuit can be operated in general mixed mode, i.e. VM, CM, TAM, and TIM, and can realize all 5 universal filtering responses, low-pass, high-pass, bandpass, notch, and all-pass, in the general mixed-mode applications without changing the filter topology. Moreover, the proposed circuit has no need of component matching constraints for VM and TAM all 5 universal filtering responses. Furthermore, the proposed general mixed-mode circuit still enjoys many main advantages, using 2 grounded capacitors attractive for integration, no inverting or non-inverting amplifiers for special input signals, no component value constraints except the CM/TIM all-pass responses, high output impedance, and low active and passive sensitivities. H-SPICE simulations with TSMC 0.25M process confirm the theoretical predictions.